Welcome to Math with EJ. In this video, I'll be talking about Laplace transform in probability and statistics. Okay. An overview of that. The Laplace transform is a widely used tool in both probability and statistics for analyzing random processes, particularly in the context of distribution functions. Moments and stochastic processes. Okay, it converts a function of time, or any variable for that matter, or any variable into a complex function, into a complex function in terms of a different variable. Typically denoted as S. The Laplace transform is defined as L of f of t of S now equals integral from 0 to infinity of e raised to minus st f of t dt, where S is a complex number and f of t is a function of time. In probability, interestingly, I have a playlist on probability. I think it has about 20 videos or so. I also have a playlist on statistics, up to 55 videos or something. I'm not too sure now. So in probability and statistics, the Laplace transform is particularly useful, is particularly useful for analyzing probability distributions and the moment. If I have a playlist on moment generating functions too, and moment generating functions of random variables. Okay, so now let's talk about, I want to switch over to this while I guess what should follow? Let's go green. Okay, so key concepts. So our key concepts in probability and statistics. So number one, we have the moment generating function, on which I have a playlist of like 15 or 20 videos. Moment generating function, M GF. Okay. So the moment generating function of a random variable x is Laplace transform, the Laplace transform of its probability density function, is the Laplace transform of its probability density function. I mean, I've taken care of all of these concepts in probability. The moment generating function of a random variable x is the Laplace transform of its probability density function, which is known as PDF for short, fx of t. So the moment generating function mx of s is the expected value of the e raised to power sx, and that is integral from minus infinity to infinity of e raised to power sx. So that's then fx of x dx. So this thing now simply tells us that the moment generating function is the Laplace transform of the probability density function. Now you see this is the probability density function, right? Of course, this is the moment generating function. So you see the moment generating function is coming from taking the Laplace of that PDF, okay? So if we can take an example, let's look at that example. Example, for an exponential random variable, an exponential random variable x rate parameter, with rate parameter lambda, the PDF is fx of x equals lambda e raised to minus lambda x, and x is greater than or equal to 0 by all means. So now we see that the Laplace transform, which happens to be the moment generating function, is now mx of s equals integral from 0 to infinity of e raised to minus sx lambda e raised to minus lambda x dx. And that will just give us lambda over, by the time you do all of that, you have lambda over lambda plus s, and that happens for s greater than minus lambda. Okay, so this is what we get in this situation. Okay, so that just goes. So we get the moment generating function by just taking the Laplace of the distribution. So I mean, if you sort this out, you're going to surely get that. I mean, I can already see that this is the same thing as, you can bring out the lambda, so you have e raised to minus uh, e raised power minus s plus lambda, and then you differentiate that. Should I worry about that? Yeah, I mean, you can work this out. Okay, let that be like an assignment. We've done this a couple of times. Work this out. Okay, work this out for sure. So lambda goes out as constant. That's the lambda on top here. And then for the rest, everything under the integral, you now have e raised power minus s plus lambda inside bracket of x dx. So if you now integrate that, you have e raised power minus e raised power minus s plus lambda x divided by s plus lambda. And that's the s plus lambda you have, which is lambda plus s. So the integral should be easy. Okay. So here we see that by taking derivatives of mx of s, which is the moment generating function, right? You can derive moments, can derive the moments like the mean, and variance of the exponential function. Okay, I mean, we've done all of this under the moment generating function playlist. Okay, so that's one example, we have the Laplace, we have the moment generating function, right? So next, let's talk about distribution function. That'll be like our number two, right? Number two. So we are talking about areas of application. We are talking about key concept in probability and statistics. So we've talked about moment generating function, which happens to be the Laplace of the probability distribution function. So now let's talk about distribution function again under statistics and probability distribution function. So we say that the Laplace transform of the cumulative of the cumulative the Laplace transform of the cumulative distribution function, which is known as the CDF, is actually related to the characteristic function, in probability theory. Okay. So the CDF of a random variable x, the CDF of a random variable x denoted by f of x is the probability that x takes a value less than or equal to x. So that's more like that's something like that. F of x is the same thing as probability that x takes a value x less than or equal to x. Basically, that's the CDF. All of this is well explained under the probability playlist. So the the Laplace transform can be applied, to the CDF, the cumulative distribution function, to analyze the distribution in the S domain. Okay, so let's take an example of that now. Example, consider the cumulative distribution function of a random variable x, which is fx of x, which represents the probability that x is less than or equal to x. Okay, so applying the Laplace transform to fx of x results in the Laplace of fx of x of the variable s now equals integral from 0 to infinity e raised power minus sx fx of x dx. Okay. So this transform is often used in reliability analysis analysis, and stochastic processes. Okay. Then the next thing we talk about is that's number 3, right? We've talked about moment generating function. We've talked about distribution function. So let's talk now about Laplace transform in queuing theory. There's just a queuing theory. Queuing, yeah, queuing theory. Okay. So in queuing theory, the Laplace transform, Laplace transform is used to analyze waiting waiting times and service times. Okay. The interval, waiting times and service times. So the Laplace transform of the inter-arrival times in a queue can be used to derive the distribution of the number of customers in the system at any given time. Okay, so as an example, in a queuing model where the inter-arrival times of customers follow an exponential distribution with rate lambda, the Laplace transform, I mean, this is very close to what we did under MGF, under moment generating function. The Laplace transform of the inter-arrival time distribution is m of s equals lambda over lambda plus s, just like what we did for moment generating function. Okay. Okay, so let's also talk about the concept of inverse Laplace transform. That's also useful. That should be the number 4 idea, right? The fourth idea. Okay, this is also what's referring to the fourth idea, which is inverse Laplace transform, which we have dealt with a couple of times in this process, in this playlist. Inverse Laplace transform. So to move from the S domain, back to the time domain, the inverse Laplace transform is used. Okay, this is essential for interpreting results, interpreting results in terms of probability distributions or random variables. Okay, so in this case now we have L inverse of f of s, and that is integral from 0 to infinity e raised to power st f of s ds. Okay, so that's inverse Laplace in short. So you can see everything is inverse, right? So this is useful. This is useful for transforming, the results of Laplace transforms back to more familiar forms, more familiar forms, such as probability densities, probability densities. So that goes. All right. So let's take an example. Should I even call it an example like that? Okay, let's switch over to this and then we go for this. So Laplace transform of a Poisson distribution. So suppose X follows a Poisson distribution with parameter lambda, which means the probability mass function, PMF, is P of X equals K, and that is equal to lambda raised to power K, e raised to power minus lambda, all over K factorial, where K is 0, 1, 2, and so on and so forth. Okay. The Laplace transform of the PMF is mx of s equals the expected value of e raised to power sx, and that is summation from k equals 0 to infinity of e raised to power sk, then lambda k e raised to power minus lambda all over k factorial. Okay, so this series is a form of the exponential, it is a form of the exponential generating function, okay, and simplifies as mx of s equals e raised to power lambda into e raised to power s minus 1. So that's like if you take the sum to infinity, of this series, this is what you're most likely going to get. So this Laplace transform helps us to calculate various properties of the Poisson distribution such as its moments and distribution behavior. Okay. So in conclusion, right, the Laplace transform in probability and statistics is a powerful tool for transforming and analyzing probability distributions, generating functions and stochastic processes. It is particularly useful for deriving moments, analyzing Q systems, and working with complex random variables in a more manageable form. Okay. Mm, let me see if we can take one or two questions. Okay, I think I found two questions that we can work with. All right, let's start with this one. No, I think we've dealt with this, so let's go for something else. This is done. Yeah, let me take this. You might find this interesting. Practice. Um, let x be a random variable. Let x be a random variable following a normal distribution with mean mu and variance sigma squared. That is the probability density function, the probability density function PDF is this popular one. Fx of x is 1 over square root of 2 pi sigma squared, then e raised to power minus x minus mu all squared all over 2 sigma squared for minus infinity less than x less than infinity. Okay, so that is what we have, right? This is sigma squared for sure. So question A, find the Laplace transform and the Laplace transform of the normal distribution PDF, of the normal distribution PDF. That's the first thing. Of course, this is question 1, right? Then B, use the Laplace transform, to compute the moment generating function, the moment generating function of x. Okay. And 3, that's C now, right? C, determine the first and second moments. Those correspond to mean and variance of x using the moment generating function. Okay. Yeah, so let me see if I can get another one. Yeah, I think I like this. Yeah, I think I really like this. Number 2, let f of s be 1 over s squared plus 4. This is actually a Laplace transform already. So A, find the inverse Laplace transform. So it's more like you're looking for f of t. Find the inverse Laplace transform of f of s. Okay. Then B, use the Laplace transform. Is the Laplace transform to derive the average number of customers in the system. In the system, that's using the first moment, using the first moment. Of course, that first moment corresponds with the mean. If you so in case you need more light on okay, I have jumped. This is not what I should be. Find the inverse, right? That doesn't seem to make sense. Sorry. Okay. So I took the B for another question. So B actually here is interpret. Interpret the result in the context, in the context of probability distributions. Of probability distributions. Okay. The hint is this resembles a sine wave function. Okay. What does that mean when it comes to probability distribution? Something uh that is like a wave. Okay. Um yeah, let's leave it there. So please let me see your answer in the comment section in Facebook, on YouTube. Let me also know if there's a topic you'd like me to teach or a problem you'd like me to solve. And feel free to let me know how helpful these videos are for you. And of course, be sure to let me know the topic. Okay, I think I've said that already, right? If you have not subscribed to this channel, please go ahead and do that. If you have already, thank you. And everybody, don't forget to hit the notification bell so you can always get alerted each time a new video is released. Then be sure to like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. In the next video, I'll be comparing the Laplace transform and the Fourier transform because they are both integral transforms. So let's see when should we use which. Bye.